So guys, today we're going to take it kind of to another level. We've looked at projectile motion problems where we shot things horizontally and they fell. Yesterday we looked at a problem where we shot things at an angle and they went up and landed at the same level that they were shot from. And today we're going to look at it at an even higher level where we're shooting off of a cliff and landing down below. Eventually we'll get to a point like in a baseball game where you hit a baseball and then it goes up and lands at a point somewhere up above like it would in a stadium up in the bleachers. Okay, but for today, let's look at this problem. Okay, so initially what's happening is we're up on a cliff and we're shooting a cannon at 30 meters per second initial velocity at an angle 75 degrees above the horizontal. And that pretty easily can be broken down into its X and Y components. 30 meters per second at 75 degrees. Our initial velocity in the X is going to be cosine 75 times 30, which comes out to be about 7.7646 meters per second initial velocity in the X. Now, just to kind of reiterate, if we neglect wind resistance, for the whole time that that thing's flying through the air, is it going to go a constant in the X direction? Okay. Constant velocity because there's no forces acting on it in the X directions. The only direction that there's forces acting on it is in the Y. Okay. Now, if we break down the initial velocity in the Y component, it's opposite the angle, so we go sine 75 times 30, and we come up with 28.98 meters per second. Now, at that steep angle, is most of your initial velocity going to be in the Y direction instead of the X direction? For sure. Okay. So that all makes sense. Now, what we're going to go for eventually is trying to figure out where that thing's going to hit down here as far as how far in the X direction it is from where it shot at the beginning if the cliff is 35 meters high. Okay? We're going to break it down into two different problems. In fact, we're going to break it into two different sections, and then we're going to do that two different ways. The first time, what we're going to do is we're going to take this up and right to this point over here as section 1, and then this is going to be section 2. Now I need everybody to kind of listen here because this is important. If I shoot this up and it's coming up at 75 degrees at 30 meters per second, when it comes up and comes down over to that exact point, how fast should it be going? Should it still be going 30 meters per second? And the only thing that's going to be different is the X component still should be the same. The Vx should be the same, but the Vy, instead of pointing up, is going to point downward, right? So legitimately, would our vector at that point be 75 degrees below the horizontal now instead of 75 degrees above it? Can everybody see that? Okay, that's pretty important leap. So let's come over here and start working our way through this. If we look at time up, which we're going to break out as being up to right there like we did yesterday, we are going to know that Vy initial is 28.98, which we calculated over there. Our Ay is negative 9.8 meters per second. And at the very top, right up there, our Vy is going to be 0. Because in the Y direction we come to a stop as we turn and start going down. If we find the time up, we can use this kinematic equation. We plug that in, the numbers in, we come up with a time up equal to 2.95714 seconds. Now guys, if that's the time up, if we wanted to find the time from here to that point right there, we just have to do what? Multiply it by 2 because time up equals time down, right? Okay. So you'll notice I multiplied it by 2. And so the total time to go from here to here is 5.9143 seconds, which, guys, legitimately is exactly like the problem we did yesterday, right? Okay? Now, if we then move and try to find the time from here down to here, we're going to use these variables. So let's come over here. Would you guys agree that our velocity initial in the Y, instead of being 28.98 upward, now is it going to be 28.98 downward? So I've made that negative. Okay. My AY is still going to be pulling down, so it's going to be negative 9.8. And the distance I have to travel from this point down to this point, is that going to be 35 meters downward, which gives me negative 35 meters. So if I am given those variables right there, and looking for the time down from that level, we should be able to say y equals v naught y t plus 1/2 ay t squared. So if we plug in what we know, negative 35, this is where I'm going to need some calculation help, I think. Make sure we get our negative. We got negative 28.98 times t dl plus 1/2 negative 9.8 times t dl squared. And guys, I think we're seeing that this is turning into something that we're going to have to use the what on? Quadratic formula. So I'm going to reset this thing to 0. So I'm going to put, this is negative 4.9, so I'm going to put that on the other side. So 4.9 t dl squared. And then I'm going to take that over there and get plus 28.98 t dl. And then that's already over there, so I'm going to go minus 35 equals 0. Right? Now I'm kind of hoping, beyond all hope, that some of you, at least one of you, has the quadratic formula in their calculator, and we can plug in our A, our B, and our C and come up with two solutions, right? Okay, so time dl is equal to what two solutions? 1.02? Is that what I'm hearing?
Yeah.
1.02, or there should be a
Negative 6.54.
6.54, right? 6 point what? 94? Okay. And then is this 1.028 I heard? Okay, let's go with that. Okay. And guys, which one of those makes sense? The positive, right? Okay. So our time from here down to here is going to be a time of 1.028 seconds. Everybody see that? Okay. So what's our total time? I'm going to go time total equals this guy, 5.9143 plus, which, guys, by the way, is the time to go from here to here, plus we just found the time from here to here, so let's add that on, 1.028, which comes up with a total time of 6.9423 seconds. So that's time total. In order to find the distance traveled downrange from where we fired to where it landed, what would we have to do now? Well, we know that distance, well, let's do this. We know that velocity in the x is equal to the distance in the x divided by the what? The time. And so if we look, do we know the velocity in the x back here? So we have 7.7646 equals x over t, which in this case is 6.9423 seconds. And then if we multiply both those, we get a distance traveled of, we're looking at like somewhere close to 50 something.
53.904.
53.904 meters. Okay. Does that make sense?
Yeah.
Okay, let's go ahead and